Hey everybody, today we're going to take a look at 7.2 verifying trigonometric identities. So similar to what we did yesterday, but a little more complicated. So let's start by just kind of giving you a little overview. One of the skills required for more advanced work in mathematics, especially in calculus, is the ability to use identities to write expressions in alternative forms. We developed this skill by using the fundamental identities to verify that trigonometric equation is an identity for those values of the variable for which it is defined. We will use two methods to verify identities. We will use the first one almost exclusively. One, work one side until it looks like the other, and two, work both sides independently and meet in the middle. So two different methods. We almost always use the first method, where we're just going to work the more complicated side until it looks like the other side, but every once in a while we'll work them separately. One thing we cannot do is you cannot treat it like an equation. What I mean by that is you can't move stuff from one side to the other. You either have to work them independently or you have to just work on one. The reason this happens is because you're trying to actually verify it. You're not trying to solve it. You're trying to show that it is an identity and that it's equivalent. So you can't just move stuff left and right. So a couple things. Verifying identities by working on one side. That's what we're going to focus on today. Avoid the temptation to use algebraic properties of the equation to verify identities, meaning you can't move stuff left and right. We can't just say, well, I have a negative sign on the left, so I'm going to add it to both sides. We can't do that when we verify identities. One strategy is work with one side and then rewrite it to match the other. So we're going to jump around a little bit, but I'm going to try not to jump around too much, but we will jump around a little bit. So it says, verify that the following equation is an identity. Cotangent theta plus 1 is equal to cosecant theta times the quantity of cosine theta plus sine theta. So I look at this and I'm going, okay, which side looks a little more complicated? And to me, it's the right side. The right side looks a little uglier. We've got parentheses, we've got a sum, we have multiplication, and there's three different values. In the left, there's only two. So I'm going to work on the right-hand side. And what I'm trying to do is I'm trying to make the right-hand side, manipulate it so it looks exactly like the left-hand side. So I got to be honest, I'm going to start by changing cosecant. I'm going to change it to 1 over sine theta. So if I change it to 1 over sine theta, I'm going to multiply it by the quantity of cosine theta plus sine theta. And now I'm simply going to distribute. And I have cosine theta over sine theta plus, well, sine theta over sine theta. And wouldn't you know it, cosine over sine is cotangent theta, and sine over sine is simply 1. We're done. That's it. That's the first identity that you verified. Again, they're not super difficult, but they take a little bit of work and a little bit of practice. The only way you're going to get better at it is you got to practice them. All right. So as we go along, they'll get a little more complicated and we'll keep going and you'll see what I mean. All right. So number 2. Verify the following equation is an identity. So tangent squared x times the quantity of 1 plus cotangent squared x equals 1 over 1 minus sine squared x. All right, so this one looks a little nasty. I still think left side looks a little worse. So I'm going to kind of work on the left-hand side and see what happens. Well, the reason I say that is because if I distribute this thing, I'm thinking something good's going to happen. So I'm going to say tangent squared x plus this becomes tangent squared x times cotangent squared x and equals the right-hand side. I'm not going to rewrite it. But remember, cotangent squared is really 1 over tangent squared. So this is tangent squared x plus, and I'll write all this out. Once you get in the habit of doing these, you'll actually identify it a lot easier and you won't have to write all this out. But that becomes tangent squared x plus 1. And I recognize that as one of my Pythagoreans. My Pythagorean is secant squared x. And I'm going, I'm getting closer, but I'm still not there yet. What if I do a reciprocal identity, 1 over cosine squared equals, oh, I think I got it, because now I can use a Pythagorean and manipulate it a little bit, 1 over 1 minus sine squared. Now, if you're like me, you kind of look at this one and go, this might, like your book says you should work one side, but this might be one of those ones where I actually work both sides, because right away I might have seen this and gone 1 over cosine squared x and then made this secant squared x, and I could have stopped here. So while your book is saying this is one that you're going to work one side on, I could actually see it being one where you work both sides. So kind of your call, but I could go either way on this one. All right, let's look at the third one. Same thing. Your book's going to tell us to work on one side, so we'll see how this goes. Tangent x minus cotangent x over sine x times cosine x is equal to secant squared x minus cosecant squared. All right, so a little bit trickier than the ones we've seen, but I think we can do it. I'm going to go left-hand side because I think the right-hand side's pretty straightforward. And on the left, it looks kind of gross, but I'm going to split this up. I'm going to say this is tangent x over sine x cosine x minus, this is going to be cotangent x over sine x cosine x. And again, this is one of those things, you look at it and you go, how the heck does he know how to do that? Well, one, I've been doing these a long time, and the more you do them, you start to recognize things. And two, this is a single term. Like, I have to distribute. There's really nothing else to do. Otherwise, I'm going to try to factor the thing on the right, and I don't really want to factor that thing. So I come over here and I say, okay, well, if I'm really doing this, this is really like tangent x times 1 over this, right? This is just another way to write this. And same over here. So this is cotangent x times 1 over sine x cosine x. And so if I change tangent to sine x over cosine x times 1 over sine x cosine x minus, this is really cosine x over sine x because it's a reciprocal, times, let's just do this, times 1 over sine x cosine x. And we multiply, the signs cancel out. I'm left with 1 over cosecant squared x minus, my cosines cancel out, 1 minus sine squared x, which is really, oh, messed that up already, secant squared x minus cosecant squared x, which is exactly what we wanted. So we verified that it's an identity. Again, the more you do these, the easier it'll be, so don't panic too much. Let's take a look at another one. We'll go to working on one side again. Notice it says verify that the following equation is an identity. And this is kind of a special one. I'm going to put a little star by here because this is one of those ones, and we encounter these every so often, that unless somebody shows you how to do this, you're not going to stumble on the right way to verify this one. This is one of those tricky ones that unless you've seen it done or somebody gives you a hint or like you're never going to try this. And the reason I say that is it's this 1 plus sine. So this 1 plus sine is kind of a tricky thing to do. What we're going to do is we're actually going to multiply the top and the bottom by 1 minus sine x. And the reason we multiply 1 plus sine times 1 minus sine x is because this is actually going to create a difference of two squares. It's going to create a Pythagorean identity, which you don't really know that yet, but you'll see it in a second. And remember, whatever I do at the top, I got to do the bottom because it's going to be like multiplying by 1. It's a multiplicative identity. And it's going to create some good stuff. And so anytime you see like, we'll put a little star over here. If you see like 1 minus sine x, or you see like 1 plus sine x, or you see like 1 minus cosine x, or 1 plus, you might want to multiply by the counterpart that's going to create a dots, okay? And the reason being is because watch what's going to happen. And again, this is why I say if somebody doesn't show you this trick, you're just never going to know it. And so as soon as I see the 1 plus sine, I'm thinking, okay, well, this becomes 1 minus sine squared x because it's a difference of two squares. I'm going to leave the denominator as is, cosine x times 1 minus, helps if I write what I say, 1 minus sine x. And what happens now is that numerator is one of those forms of the Pythagorean. That's that cosine squared x is equal to 1 minus sine, which now allows me to cancel some stuff out. And so if you notice, this will cancel with one of those, giving me cosine x all over 1 minus sine x, which is what we wanted. Again, this is one of those things, unless somebody shows it to you, you're not necessarily going to recognize it right away. So keep that in mind. If you see 1 minus sine, 1 plus sine, 1 minus cosine, or 1 minus cosine, you're going to use one of those little tricks. Okay. I know I have a couple more here, but I'm going to save those for class. I'm going to jump ahead to working on both sides. And we're just going to do one. We'll work on both sides on one, and then we'll save the rest of these for class. So verifying identities by working on, it says both sides, but it should say both sides. Sorry for the typo. We did this a little bit in one of the earlier ones that I showed you. You could work on either side, but here's kind of how it looks. If both sides of an identity appear to be equally complex, the identity can be verified by working independently on the left side and the right side until each side is changed into some common result. Each step on each side must be reversible. With all steps reversible, the procedure is shown below. The left side leads to a common third expression, which leads back to the right side. So working with both sides is often a good alternative for identities that are difficult in practice. If working with one side does not seem to be effective, switch to the other. Somewhere along the way, it may happen that the same expression occurs on both sides. So again, these typically when you'll work on both sides. When you start working on one side and just get really frustrated, and you'll jump to the other side and start working on it, and you'll find that both of them actually became equal. So here's a perfect example. Left side and right side both look terrible. I've got secants, I've got a trinomial, it just doesn't look good. So let's do a couple things. On the left-hand side, I'm actually going to turn this into a complex fraction and rewrite it in terms of sines and cosines. And that's something from 7.1 that is carrying over into 7.2, that when things look really bad, maybe try writing them in terms of sines and cosines because they're a little easier to work with. So this is 1 over cosine alpha plus sine of alpha over cosine of alpha all over 1 over cosine alpha minus sine of alpha over cosine of alpha. Sorry, my alphas look terrible, but is what it is. Okay, so we'll pause there on the left-hand side. And I actually like working on both at the same time. There's some people who like to work just the left and then just the right, but I like working them at the same time to see kind of where they're leading. That top one is actually, believe it or not, is a TPS. You can factor that thing. And I know what you're thinking. You're going, oh my Lord, are we really doing factoring with this? Yes, we are. That stuff from way back when in Chapter R just never seems to go away. So 1 plus sine alpha quantity squared over cosine alpha, cosine squared alpha. All right, so I've simplified the left a little bit. I simplified the right a little bit. So now let's look back at the left. You'll notice complex fraction. All the denominators are the same. They're all cosine alpha. So I'm going to multiply the top and the bottom by cosine alpha. So on the left-hand side, I end up with 1 minus sine alpha. And underneath, I end up with 1 minus, the numerator is plus, and the bottom is 1 minus sine alpha equals. On the right-hand side, I'm actually going to take cosine squared, and I'm going to manipulate it a little bit because when I start to look at the left and the right, I seem to notice that like the numerators are pretty close. It's the denominators that are a problem. But this denominator is actually hinting to what I need to do to cosine. That cosine squared, I actually have to rewrite. So I'm going to get rid of some of this stuff. I'm going to say, okay, numerator's the same. 1 plus sine alpha quantity squared over. This is that manipulated Pythagorean. It's really 1 minus sine squared alpha. And you're going, okay, well, why does that help? Well, 1 plus sine alpha over 1 minus sine alpha. If I factor that now in the bottom, 1 plus sine alpha quantity squared, this is a dots. This is 1 plus sine alpha times 1 minus sine alpha. And you'll notice this will cancel with one of them. And now I have the exact same thing on the left, 1 plus sine alpha over 1 minus sine alpha, as I do on the right, 1 plus sine alpha over 1 minus sine alpha. Again, not super fun, but not terribly difficult once you kind of learn how to do it. Again, best way to learn these is you got to work on practicing them. The more you work with them, the easier they will be. We'll continue working on them in class. Have a great day.